Thank you, everybody, for being here today. So my name is Shankar. I'm from NetApp. This is Pranup. He's also from NetApp. And we're going to talk to you today about some of the lessons we've learned with our analytics system, walk you through what we do with the data, what are some lessons we learned, and what we're doing now. And let's keep it interactive. I think the usual style is to ask questions at the end, but feel free to interrupt at any time. OK, so here's what we're going to talk about. We're going to talk about what is this thing called Active IQ, which is the application that uses all this data that we gather, and what kind of data do we gather. Then we're going to talk about just 5 data management challenges that we have. Well, we have a lot of challenges in general. As those of you that deal with Hadoop and data science know, there's plenty of problems. But we're going to focus specifically on data management. And then talk about a hybrid cloud architecture we have in place that we've been running for the last year. And then Pranup's going to talk about why NFS for Hadoop, right? Should we start thinking about shared storage again? And then we'll talk about some software we have done to enable this. So, before I continue, there's one thing I should say. Because I've spoken about this in other forums in the past, and often people will say, well, you guys are NetApp and NFS, so no wonder you're talking about NFS. But I should tell you that the group that I work for, the data engineering, data science team, we are chartered with getting insights for our customers. And we are free to do this with any storage, any compute that we need, right? So this isn't really that we work for NetApp and therefore we're talking about this. This is what we found to be useful. So we have this telemetry system called auto support that's been around actually a very, very long time, since 1995, long time. And we get 3 kinds of data every single day. Configuration data, right? What are people doing with our storage systems? How are they configured? Performance counters, and logs. And logs are your traditional Unix system logs. We get this every single day at the bare minimum. Some of our newer systems send data every 5 minutes. Okay, it's a lot of data. And all of this is part of a larger ecosystem called Active IQ. We do a bunch of things with this data. So we basically make the insights from this data available to all our customers. You can't read it, but that's the desktop application on the right called Active IQ that presents this data and the insights to customers. It's also a mobile app. But here are some interesting things we do. One is we predict disk failures, right? Because after all, we sell storage systems, and we sell lots and lots of disks and now SSDs. And as you probably know, these things do fail. So we'd like to get ahead of this problem and predict when something is going to go bad, and then replace it ahead of time. And today, that's become a fine art. In fact, the entire thing is completely automated through our system. We will actually get a telemetry message, process that in under 2 minutes, make a prediction. If we decide that the disk is about to fail, we actually send another electronic message to manufacturing. They procure a new disk, slap on a FedEx label, goes back to the customer. There's no human involvement at all. The other things we can do is, we can predict performance problems, a certain class of performance problems ahead of time. We have a very sophisticated rules-based system that's been built over the years that can look at all our storage systems, look at this telemetry data, and decide whether something is misconfigured. Our support people use this telemetry data constantly, so anytime there's a customer case, some complaint about something, first thing they do is go look at this telemetry data to diagnose the problem. And where we are headed really is, we get data from so many different customers, so many different systems. So there is some sort of community wisdom in that data. So how do we use machine learning and deep learning and detect this community wisdom and inform our customers how they can use our products in a better way? That's really where we are headed. OK, so this is some stats on the data that we have. So we have about, we process 70 billion data points a day. This number is already outdated. So our data is growing about 2x every 8 months. And some of these things are growing, doubling, even faster than that. In terms of the volume of data, it's not an awful lot. It's about 135 terabytes a month. All of this is stored in a 4-petabyte data lake. It's a Hadoop data lake. And because our data is growing so fast, that data represents smaller and smaller periods of time. Right? Today, it represents about 2 years' worth of data. But we'll get to a point where it represents just 1 year worth of data unless we expand it. Okay? So what are the 5 challenges we've seen with data management for Hadoop? The first problem we have is our storage is growing. Our needs are doubling literally year over year. And for a while, our answer was, let's go buy more storage. Well, we're a storage company, so it's not that hard. But this is a problem for a lot of customers. The second thing was we needed to get to the cloud in a cost-effective and secure manner. I should probably preface this whole talk by saying today we are doing Hadoop on premises, but there's an interest, like most people, to get to the cloud. The third problem is as we start doing more machine learning and deep learning, we realized we have separate architectures for AI and a separate architecture for Hadoop, and those need to come together. Fourth problem is there's lots of different sources of data. So in any modern data science effort, it's not just what's in your Hadoop data lake. There's a gazillion other databases that contain interesting data, right? There could be things on the web. And how do you pull all this together seamlessly and blend it, right? And the last part, which I think the Hadoop community has really not addressed well, is the need for data provenance. And by that, I mean that we'd like to understand for any piece of data what its origin was. Where did it come from, and what were the computations that resulted in this piece of data, okay? So I'm only going to cover the first 3 in the interest of time. So this is a traditional view. This is a very, very high-level view. You may not have anything that looks exactly like this. But essentially, this is what a lot of companies have on-premise. And we have some variation of this, right? You have some input telemetry data. People very often use Kafka. There's NiFi. There's a whole bunch of things there. And you typically have a real-time cluster to process data as and when it arrives. And you have a data lake where you maintain historical information to look at trends over time. Now, the first question you might ask is, why aren't these the same thing? Why don't you have a real-time cluster and the batch processing cluster combined together? Now, there's a move towards doing that, but the fundamental problem is that Hadoop doesn't do a very good job of separating I/O for different workloads, right? So if you want quality of service, this isn't easy to do, right? And then this data gets ETL'd into various data stores, structured, unstructured, and you build your machine learning models on the curated data. So this is a very high-level view of what's going on. So what's the problem with this? So the first problem is the problem caused by storage growth, right? In your typical Hadoop cluster, and here I'm going to talk about direct attached storage, right, which is your traditional model. You essentially have a server which has some CPU memory and attached disks. You're making 3 copies of the data. Now, of course, with HDFS 3.0, you have erasure coding, where you don't have to make 3 copies of the data, but you would typically not do that for performance reasons. Now, as you keep increasing the amount of data that you have, you're throwing together this compute, right, because it's direct attached storage, and that compute really has no purpose there. It's just because the way the system was built. And we have met a lot of customers that have told us that they have 1,000 and 2,000 node Hadoop clusters, but really they needed only about 500 nodes for the compute, right? So that's one problem. Now, the second thing is when you have very large Hadoop clusters, you are going to have disk failures at that scale. And more insidious than disk failures are something called latent sector errors, which the community doesn't, I feel, understand really well. But essentially, disks have this way where certain sectors can go bad. Now, you would detect that at the time of a read, because the checksums wouldn't match, and you can recover from that. But the trouble is, when you have 5,000, 6,000 disks, this is going to be a very frequent occurrence. So some fraction of your Hadoop cluster's computer network is just being used to reconstruct bad data. The third thing we've noticed is people end up with a lot of different Hadoop clusters. They have one for QA, one for pre-production, production, and so on. And they're just copying this data all over the place, right? It's the same data, right? So very soon you have 10 copies of some fraction of the data. And the last part of this is, there is tiering that's there in Hadoop, but it's not self-managing. You actually have to be pretty smart about how you manage it, okay? And like I was saying earlier, you can't really set quality of service on storage in Hadoop. In other words, you can't say, this workload needs this much guaranteed throughput, and that workload can take less throughput, right? There's no way to do that. You can play games with yarn, but that's the best you can do. Okay, so see, these are some of the problems that we have observed caused by storage growth. And so, so we said the first thing we need to do is separate compute and storage. This isn't a new idea by any means, right? This has been there in academia since, 2009. People have been writing papers about this. But here's the thing. And also, I should point out that if you're running Hadoop in the cloud, your compute and storage is separate anyway. You're separated by a network, right? Now here's the thing. When Hadoop was invented in 2006, the networks were relatively slow. You had gigabit Ethernet in the data center. Network latencies were pretty high. So you had to keep compute and storage next to each other, both to get good bandwidth as well as to get low latency. But that's just not true anymore, right? So the latency in the network today, right, has reduced considerably. So today with 40 gigabit Ethernet in the data center, the latency across a switch is less than 5 microseconds, okay? So there is really no latency problem anymore. And what about bandwidth? Well, a modern all-flash array, a storage system which just has SSDs in it, can deliver 25 gigabytes a second throughput, right? If you were to build your Hadoop system using, regular disks, right? And I know I'm comparing apples and oranges. One is SSDs, other is disk, but just bear with me for a moment. If I built these regular, Hadoop clusters, I need 350 of these nodes to get to 25 gigabytes a second, okay? So bandwidth's not a problem anymore. Latency is not a problem anymore. So there's really no reason to keep your compute and storage next to each other. Okay, so here's the second problem, which is making the decision between being on-premise and the cloud, right? So some companies start by being cloud first, and that's great, and it works to a certain scale. But the traditional enterprises typically have started on-premise, and now they're struggling with what do they move to the cloud. Clearly, there's a need to get to the cloud, right? And there's many benefits that I've listed there. But one of the questions that comes up often is this cost-effective and is it secure? And I think security is more a psychological problem than a real problem, right? There are ways to solve that in the cloud. But there is a prohibitive cost to putting data in the cloud, especially at large scale. We work with some companies that are building connected cars, and they are gathering about 400 petabytes a year of data, right? That's 400 petabytes. Now, just think about putting that amount of data in the cloud. You're pretty much going to go bankrupt, right? We've done the math with like 10 petabytes of data, various kinds of storage. It's quite expensive. And then here's the other problem. You have to pick a cloud, and once you pick a cloud, you're kind of locked in because, the cloud provider's ingress of data is free, egress can get expensive, right? But yet we want to use the cloud, so how do we do this? So what we have done is essentially a solution. We call this cloud volumes, which is storage as a service that's in a colo facility that's close to these clouds, right? So Amazon has this thing called Direct Connect, Google, Azure, they all have these things. Essentially direct connections from the clouds into co-located data centers. So that keeps your storage safe, and you can have this connection at very low latency, 1 to 2 milliseconds at best, closer to 1 millisecond. And you can also get very high bandwidth. You can get multiple 10 gigabit links and more recently 40 gigabit links from the cloud providers into this cloud connected storage, right? So this gives you the freedom to use the storage that you want, but without the sort of security risks or the lock-in by entering a particular cloud. Okay. So what we did is, in our ecosystem, we said, well, we want to use the cloud. Our data scientists want to use the cloud. We have a lot of bursty workloads, right? So for example, we had a cluster for a Hadoop cluster for QA, another one for pre-production. And we looked at the utilization numbers on those, and they were really low. We said, it makes no sense to put this on-premise anymore. So let's get to the cloud. So what we've done is anything that's 24/7 that requires very high throughput stays on-premise. Okay? For example, our real-time processing and our batch data lake, which needs very high throughput, stays on-premise. But anything that's bursty in nature, we run in one of these clouds. Okay? So for example, our Hadoop QA, today an engineer in our team can essentially, once they check in some code and they click a button, we can go off and dynamically spin up a Hadoop cluster in any of these clouds, attach to the data in these cloud volumes, and make all of this work, right? And it takes less than 5 minutes to do this. Okay. Same thing with machine learning, right? Our data scientists now have freedom to pick whichever cloud they want, connect to this data in these cloud volumes, and do what work they need to do. Okay. So the third challenge I'm going to talk about is the right storage architecture for AI. Now, this is a fairly complicated topic, and in the interest of time, I won't go into too much detail. I'm happy to talk about this offline. Hadoop and HDFS in particular was designed for sequential I/O, right? Large block sizes, lots of large files, right? It's throughput oriented. But when you look at what's going on with AI, it needs IOPS more than throughput. Okay? People are typically using a shared file system for distributed training, and the focus is more on random I/O than sequential I/O. So the two don't match. All right? So very often what we find for people that are really doing serious AI, they are curating their data with Hadoop, right? Cleaning it up, doing ETL, and then they have yet other infrastructure for AI. And that's not something we wanted. So what we decided to do is to solve all of these problems, right? The storage, to separate compute from storage, to have the same architecture for both AI as well as Hadoop. We decided to combine all our data into one source, one unified data lake that actually is running NFS. And when you first look at this, you might have a bunch of objections. You say, well, how is this going to work? Because NFS is not HDFS, right? Won't the latency be too high? Will you get the right bandwidth, and so on? And we've solved some of these problems. So Pranup's actually going to talk about how we solved this using a piece of software that we wrote. And today what we have is an ecosystem where you can spin up a Hadoop cluster, running Spark or MapReduce, Hive, whatever you like, connect to this unified data lake over NFS. And at the same time, you can also do your AI stuff. Like, for example, if you have an NVIDIA DGX server, right, which by the way, talks NFS, you can connect to the same data using this. So it's one single unified data lake. It also has the ability to tier storage automatically, because when you have petabytes of data, there's no way you're computing on that all the time. You have lots of different tiers. All of that is auto-managed in the system. We can rapidly clone data. So for example, if you want to do QA, right, we don't actually have to copy the data. We can just do a clone and create a new Hadoop cluster and point at that. Okay? We also have compression that's inbuilt, so that you don't have to use your Hadoop nodes to do any compression. And the most important thing is, as disks get larger and larger, right, especially when you have disks that are greater than 4 terabytes in size, the chances of having failures and these latent sector errors is very high, right? And we do a form of erasure coding within the storage system itself to protect against that. So net-net, we have a unified data lake on which we run all our different workloads. And with that, I'm going to switch over to Pranup, who's going to tell you about this entire architecture.
The clicker. Right. Thanks, Shankar. Just to go back to this last slide, as you can see, the NFS is the centerpiece of this architecture, right? I mean, shared storage exported over NFS. But if you look at this picture, I think you see multiple dimensions of efficiencies built into this architecture, right? One, NFS shared storage, it separates storage and compute obviously, right? But more important thing is here in this data lake that unified data lake that we built, exported over NFS, we can optimize the storage footprint between active and inactive tiers, right? The unified data lake actually is built on top of our platforms that support Flash as well as HDDs. But we can also tier the data seamlessly without any disruption to your existing data management workflows to object stores in the backend. That's number one efficiency. Number two, we also made a case for cloud-connected data center, just because the sheer amount of innovation happening in the cloud, and you want to be able to leverage some of these machine learning algorithms, et cetera, there, we need to be able to seamlessly transfer the data from on-prem to cloud, right? And that's actually enabled by NetApp Data Fabric, which is a very storage-efficient data transfer engine. The storage efficiency that it learns from the on-prem, it can transfer the same amount of data with storage efficiency built in all the way to the NetApp cloud volumes in the cloud. And number three, the multiple advantages to having this architecture. With this architecture, we were able to see almost like 12x reduction in storage space. Right? There are two components to that. One is by eliminating HDFS 3 copies and having a single source of data here on the unified data lake, we actually can cut down the storage footprint by 3. I mean, 3 is more of a, probably being more generous, but 2.5 is probably more because we use RAID in the backend. On top of that, these shared storage backend have efficiencies built in, inline as well as the background, like compression, dedupe. We were able to see around like 4:1 storage efficiency, and that's where this number comes from, which is 12x storage footprint reduction from the old architecture. The second one is the 30x improvement in performance. By centralizing your storage on a single architecture and be able to tier the cold data to the object stores, and the fact that you can actually even put in some flash memory in there to actually accelerate your compute, read compute. If you look at most of the analytics workloads, they are mostly read. And we were able to actually see a huge performance gain there. Even on the HDD or hybrid systems with HDDs, you'd be able to put some flash memory there and be able to get a lot of read IO throughput. And of course, we were able to reduce 3 copies of data by putting it on NFS with 1 copy. And that also allowed us to reduce the overall compute requirement on our compute farm. So I know we, as NetApp, will continue to pitch NFS, but like Shankar said, he is actually one of our internal customers to us. Whenever we have a new workload, we actually evaluate the fit for NFS in multiple dimensions. Right? There were days like 5-6 years ago, NFS was nowhere in the play in the HDFS world. Customers who are experimenting with Hadoop, they would just use provision a compute cluster with HDFS in there and copy the data and then be done with it. But the scale of data and the performance required out of this data, right, for your real-time analytics or machine learning, actually sort of people have a perception that NFS is not ready. So we had to really look at the fit from all these multiple dimensions. And number 3, the third dimension is actually the manageability aspect. This is important because if, for a data scientist or a data engineer who's used to Hadoop, I don't want to be going and teaching them NFS, right? They should be able to simplify this deployment for themselves, without actually involving like, your IT or storage admin. So let me evaluate the fit of, scale out NAS from these 3 dimensions, and then we'll go and talk about how we've been able to achieve that. So NFS performance. A lot of people, I think, even today, I think a lot of people I meet tell me that NFS is slow, right? Perception is that SAN is faster, they can do 16 gigabyte per second, etc. But we have systems built that actually can give you under millisecond latency, right? 500 microseconds is the sort of the optimal point latency at which your performance is very predictable. We can do 25 gigabyte per second throughput in a single HA pair. HA pair is basically for cluster resiliency. And with the emergence of scale-out NAS, to deal with the volume of data that you're seeing, 24-node cluster can actually scale up to 300 gigabyte per second. I mean, these numbers are nothing to sneeze at because, for the most part, most of our customers haven't really reached these limits yet. And this will continue to improve because the systems are getting more denser. They can pack more performance with SSDs, flash, etc. So, storing data for analysis, machine learning, real-time analytics on shared storage actually is a very, very valuable proposition. Second, let's talk about scale. I meet customers and a number of industry folks who actually continue to say that, oh, NFS file systems have limitation in size. We actually can build a file system, single file system. You have distributed file systems. HDFS is a pretty big distributed file system, optimized in one dimension. But scale-out NAS is optimized in all dimensions for sequential workloads, for random workloads. But they can also store a lot of capacity. A single file system can scale up to 20 petabytes. And one of the challenges with HDFS is the number of files that you can support because of the presence of the metadata node. It doesn't scale very well. You're talking about millions of files. We actually can scale to 400 billion files, and that is the tested limit. And if you look at the supported bar on the lower side, we actually can go up to 4 trillion files. I mean, we haven't been able to find a workload that actually needs that many files. So it's important to understand that NFS can scale. I mean, the scale-out NAS can scale. And I think most of the solutions out there can scale today, but our product also can scale to these dimensions. The third aspect is manageability, right? Like I said, Hadoop evolved from the perspective of HDFS evolved from the perspective of Hadoop, with a lot of batch processing as the primary workload. Over a period of time, there was a file system layer built to connect to various data sources, data lakes, and of course there was one thing missing there, which is like NFS. And that is what we built, in-place analytics module. We call it in-place analytics module. And the idea is that, when a company like NetApp is going to look at this and say, for example, take an example of auto support. We have had auto support for the last 25 years. And when the data comes in from customer endpoints, we actually put it on NFS for internal sharing, right? So that multiple admins can run some data on that, some analysis on that. So for us, it was obvious for us to actually just provide NFS connectivity to the Hadoop data lake, so that we can run the analysis tools, right? So initially we started with HDFS like everybody else with a small set of 10, 20 compute nodes. But as we provided the NFS connectivity from this, we were able to glean the data from NFS directly without copying into HDFS again. So it's actually available as a drop-in jar file. It's nothing but is a file system implementation. We implement NFS operations through that file system Java API connected to the Hadoop API. Very, very simple configuration. You don't have to do anything other than just specifying the path. And this is the simplicity I was talking about. We don't want to be teaching NFS to our analytics customers, Hadoop customers. We want to be able to just make it seamless for them, so they just go to this JSON file with and change the path from HDFS path to the NFS path, and your data is available for analysis. And we can actually integrate with the LDAP directory services, so there's some level of security there. We are further enhancing this with Hortonworks support, where putting in Ranger support for your data sort of security rights management, right? Who gets access to do what on the particular data lake. And we have our own NFS semantics of Kerberos that actually will come in where data is more secure and encrypted. We intend to provide further full compatibility for HDFS so that some of your daily tasks that you do with HDFS be able to query the file system information, etc., will be available. That APIs also will be available. Now, what are the additional benefits of NetApp in-place analytics module? So Shankar has talked about, okay, so all these things have to come together for you have a seamless implementation, right? And I think that was Shankar's requirement. The primary benefit by layering the NFS file system Java implementation below the file system layer was that your existing applications would run seamlessly as long as your data is available in the NFS, number one. Number two, no copy sprawl, right? I mean, you're getting direct connectivity to NFS. You don't have to copy data into HDFS with your local desks anymore. And we talked about performance and capacity. Your data lake could be as big as 20 petabytes, and you can get up to 25 gigabytes per second on a single HA pair. Number three, leverage data management. So data management may mean something different to you, to the Hadoop world, but we have been breathing and living data management for the last 20, 25 years. For us, data management is managing your backups, your disaster recovery copy, right? and be able to clone when you really want to clone a file system to provide test and dev sort of facility to the customers. So snapshots also for your built-in resiliency, so that if you accidentally delete a file, you'll be able to find that in the snapshot. We want to be able to leverage customers to leverage their data management principles, our data management principles, to be able to deploy a fine analytics architecture. And by that, what I mean is, a customer says, hey, I mean, I want to collect a snapshot every night. I mean, that's what our customers typically do. But you know what? I don't want to really run analytics on the latest copy of data or the data that is changing in the next day. I want in the last snapshot, right? So they should be able to access the snapshot directly through this connector, and that they'll be able to. Same thing about clones, right? Point in time. You want analytics at a point in time, tonight, tomorrow, or you want to fork off another file system to give it to your end customer. And that facility is available through our NetApp storage architecture and is exported through this as well. Number 4, optimize for streaming throughput. I think anywhere I go, I typically hear NFS is not good for streaming throughput, right? But with the innovation around Flash and the point that Shankar made about network, the speed of networks, sequential throughput is not a big deal anymore. And I think further we have built in some mechanisms in the in-place analytics module, whereby for sequential workloads, which actually HDFS is known about, and if you already have some legacy data on HDFS, we do a lot of multi-pathing, meaning we can talk to multiple network endpoints at the same time to fetch the data in parallel. We do a lot of concurrency. I mean, sequentials, you need a lot of prefetching of data, right? So that if you're acting on a file that was 1 gig, we actually built in a lot of prefetching into that. And one of the challenges with NFS that people tell me all the time is about, okay, hey, NFS has a lot of metadata. Not like SAN, it's like block, I can just put a block and get a block. But with NFS, data and metadata proportion is high. So we have actually built optimization where you can reduce the amount of metadata, the IOPS actually that generate out of this Hadoop stack. And more importantly, NFS and HDFS can coexist. As you can see in the last picture, it is actually nothing but implementing a file system API. So you could use NFS for primary and HDFS for secondary, or vice versa, right? So it's a choice you get by actually installing this module, right? That's all I had mainly on the module and how we were able to actually make that happen in our architecture, right? That's the primary underpinning of our architecture. Be able to provide shared access to the data, one copy of data exported to multiple sources through HDFS, through directly over Linux NFS. We were actually able to, of course, transfer the data efficiently to the cloud, to NetApp Cloud Volumes, where you can analyze the data with the latest and greatest tools that are available in the cloud. And number 3, deal with multiple sources of data with access own rights. If you were to as and when we support the Ranger, you will be able to manage the rights management with your data as well. So just to summarize this, based on our own experience, I mean, this is not something that we came up on day one. I think it's learned out of experience from the volume of data growth that actually Shankar talked about. We believe actually the disaggregation of compute from storage actually is the right choice for architecture. Building a unified data lake actually will save you a lot from a perspective of the total cost of ownership, because one copy of data exported into multiple means with a very, very performant backend. And of course, we efficiently transferring data to the hybrid cloud, to the cloud, with access to your cloud innovation is actually another additional strength of this architecture, right? Which we believe actually will position us for the long term. Okay, and that's all I had. Any questions?
So I'm just curious, show of hands, how many people are running Hadoop directly in the cloud, like nothing on-premise? Okay. And I guess the rest of you are doing something. How many people are hybrid, doing something on-premise and partly in the cloud? Okay. So do you all have an opinion about, so this is what we have, right? Let me pull up that slide.
Go back. One more, yeah.
For the people doing, hybrid, do you all have strong opinions about this? Do these problems that we shared actually resonate with what you have? How many people agree? How many people agree that these problems exist?
How do you, like you said, your QA and engineers can siphon off data for one-to-one clusters, right? That would still require a copy from your cloud volumes to the S3 or DC storage.
No. So okay. So question was, how do the QA people use the cloud, right? So the cloud volumes are essentially NFS as a service. Just like you would go to Amazon and you click a button and you get an S3 bucket. Here you click a button and you get an NFS volume. Using that software that Pranav spoke about, that in-place analytics model, we make NFS appear like HDFS to, for example, if you're running Hortonworks in Amazon, right? It would, this NFS volume, this cloud volume would appear to be like HDFS.
Right.
You don't have very data-intensive operations running on the cloud, right? Because I'm assuming with that, you're going to siphon off data from these volumes to the cloud every time. It's going to be a network cost. And
Right.
if you have a data which is read by a lot of different processes, right? Your whole idea of saying that network is unlimited or it's not no longer a bottleneck would be difficult, because if I'm reading the same data 10 times, then like the volume just grows 10 times.
So the question is the network effect between these cloud volumes and these cloud providers, right? So yes, we don't do anything that's extraordinarily intensive. So there are limits, right? But here's the thing. So a direct, so if you go to Amazon, they call it direct connect. Azure calls it express route. These links are 10 gigabits a second, okay? So essentially, if I have 4 links like this, that's 40 gigabits a second. That's a decent amount of throughput to do a lot of things. So which is why we do our QA, our machine learning model building, all of that in the public cloud. Now we wouldn't run a 500 node Hadoop job in that architecture, right?
Also to keep in mind that the overall data lake might be 3.7 petabytes, like we shared as an example, but the active data is 135 terabytes. But a proportion of that is a portion of that is going to be useful in the cloud.
So we made we.
Might be slightly difficult because you want to run actual workloads in the cloud. You're going to span or at least query a lot of that 135 terabytes that you have active, and it's not going to be like a very minuscule.
So it depends on how much aggregate bandwidth you have, right? You can do the math. So if I have 40 gigabytes a second, that's how much aggregate bandwidth, right? But we actually spent a lot of time thinking about what if we just put everything in the public cloud, didn't do anything on premise, right? See, even if you didn't have this network is actually a red herring. Even if you're in the public cloud completely, there is still a network. You just don't see it, right? Because let's say you have your compute instances and your storage. There is an internal network. And we've done actually measurements over the course of a day. What people don't realize is, A, your bandwidth's actually not that high, right, for storage in the cloud, for a variety of reasons. The second thing is it varies greatly by time of day. If you run, look at that storage at midday Pacific time, you'll get half the performance as midnight Pacific time, right? So it's not as big a problem as people think it is. But we did all the math. So if we'd gone completely to the cloud, costs were just enormous. It seems to be very effective for things that are bursty in nature.
Okay.
Yeah.
Question.
Okay. Okay. So I have not looked at that in detail. I should go look. But here's the thing. It was a general statement that today, if I get a piece of data in like, say, let's say someone used our Hive data, ran a bunch of SQL queries, did some data transformations, and wrote the data somewhere else in HDFS. If I look at that file in HDFS and I say, what was its origin? How did it come about? Okay. Okay. I'll have to go look at that. Okay. Okay. Yep. So it actually lives on both sides. The question was traditional BI, where does it live, right? a lot of it lives on the left side, but you see this right side, what's in this cloud volume is actually a copy of the data lake. Not an entire copy, but the last few months. So we actually do have some BI people saying, you know, there's some new tools I want to try that's not there on premises. I'll go spin it up in the cloud. So it actually happens in both places. Yeah. Technically, yes. It's officially self-service, but in practice, nothing is ever self-service. Yeah. Yeah. You mean, how do we address their concerns about the telemetry data being private, right? Good question. So
Is it due to the transfer of data, or is it actually the data at rest? Talk about that. Well, you could encrypt your data in the cloud. I mean, I think that's what we tell customers, and some customers do that.
So yeah, so that's a good question, and it's not a straightforward one to answer, because no matter what you tell your customer, there'll always be something they're not comfortable with, right? Okay, so everything that's on-premise, on the left side, they're pretty comfortable with, right? It's within our perimeter. It's the right side, they get a little uneasy. Like Pranup was saying, everything in those cloud volumes is encrypted by default.
Right.
Okay. Now, there's still questions about, you know, can someone hack into that stuff we're running in the cloud and access the data? We run everything in there. It's not in the picture in VPCs, right? And we do a bunch of things. We make sure there's no internet gateway attached to the VPC, and you know, calls get proxied through a particular tunnel and all that. So we do a bunch of things to make sure the data will never leave that right side of the picture, but it's not an easy conversation.
I mean, just to get into specifics, this data fabric is a very, very optimized replication engine that is actually could be layered on a VPC, I mean VPN, right, where you can encrypt your data, right? And cloud volumes are already encrypted, right? And this path can be also, you can support Kerberos with encryption there, so that your data is secure end to end, all the way to your compute.
But remember, this is telemetry data. This is not the customer data, right? It's more about the configuration and logs and such. So there's a little less concern about the privacy of that data. Yeah. You know, like to give you an example, so many people that work for large companies here do business with the US government, right? And they have their own restrictions, right? So yeah, it doesn't work for everyone. Anything else? Okay, thank you.
Thank you.